Hello everyone. Today I am going to deliver another lecture on vibration control. So first of all, I will see the classification classes of the structural control, which is passive, active, and hybrid control, and shear wall. And then third, we will see the base isolation system, which is including elastomeric bearing system, sliding bearing system, and then we will see the TMD, which is tuned mass damper, and TLD, which is turned liquid damper. And then we will see the hybrid control, which is a hybrid mass damper system, and uh, magneto magnetorheological damper. And finally we will do the practice problem. So we can see rather than number point 7, all are the theory. These are the theory, and last one is the which is the practical problem, which is experimental or is a numerical, which is example. We'll emphasize the number 7. Before going to the 7, I will discuss the all of the up to point 6. So let's start the classes of the structural control. So this slide is taken from Professor Dr. Iftikhar Anam sir, which is professor in University of Asia Pacific. Okay, let's see. Here is some explanation which we have been seen here. In order to protect the structure against the extreme stresses or to control the exceptional vibration, impose the dynamic load or incoming wave, and the structural properties may need to modify, such as measure are the called vibration control. Although basic idea of vibration control or stress control has been instrumental in development of most structural form in ancient types, the vibration control has developed as an active field on the study only since 1970. Okay, let's see some. However, the measure of can be divided into following classes of the structural control. Number 1, passive, and active and hybrid. The passive, where the vibration are controlled by some building modification or additional structural element that change the structural properties or load acting on it. Some modifier to stiffness, mass damper, or structural used to passive controller devices. Okay, and then we can see the active control, where the motion are modified by action and control, some activated by external energy supply. The control of force function of structural motion, so structural vibration are controlled by feedback system. And then last one, the hybrid control, a combination of passive and active control system, which incorporate advantage of the both. Passive system are more reliable, do not require additional energy source, but occupy the large space and can be instructive. Moreover, they are not effective against all type of load or similar load or different frequencies. So we can see you can see here the active control. Passive, that means structure will be in passive control. Um, will insert something on will insert something on a structure, but structure will be it will be come, and this is the very cheapest. And another one we can see here, we can see that another one is active, which is called when the hazard will become, then the electronics device will be started, that is called active. And hybrid, it will be passive plus active, but it will be less cost, they are active. And in three of them, active control is very much what I will say, very much costlier, but we can use the passive control, as we can insert something on the structure. Okay. Uh, okay, we can see here passive control. So we'll emphasize the passive control rather than active control. It's very cheap here, any kind of. So let's see the passive control, which is cheapest way. So you can see the passive control essentially enhance the ability to structure dissipated energy to reduce the displacement demand and reducing demand in conversion structure. So you can see here figure effective base isolation, or you can see base isolation is induced here. Another is a bracing frame, which is CBF and EBF. The brace is induced. Another was TMD and TLD. We have been seeing this is the TMD, tunic mass damper, and tunic liquid damper. You can see. Okay, so passive control we've been seen most of the devices. So device are so one, the device is modified to stiffness induce the base isolation system, which are essentially flexible spring, and to foundation take the structure flexible and reduce its natural frequency significantly. And another is control device with modified damping is system is includes various viscous damper, which is operating principle of the fluid flow through the orifice. Okay, we can see the device like TMD, which is tunic mass damper, and TLD, which is tunic liquid damper, and tunic liquid column damper can put into categories. The producing external dynamic forces consist of their own natural frequencies. It can be turned in match expected frequency vibration. Okay, in this way we can complete it this. So now we'll go to the shear. Number two is a shear wall. So these are the showing the shear wall in building. The RC building often have the vertical plane like RC wall is called shear wall. It's bigger. We've been given here. This is the plane. Okay. So architectural aspect of shear wall, we can see here the unsymmetric location of shear wall. This is the shear wall. These are the shear wall. This is the unsymmetric, and the symmetric of building in a plane about both axes. So this is the symmetric. This is shear wall. This is shear wall. This is so symmetric and unsymmetric plane in shear wall. You can see here. The possible geometry shape of the shear, we can see here the hollow shape. Here is the C shape. There is the L shape, and this is the I shape. You can see. Okay. Now we'll go to the we've completed this. Now we'll go to the base isolation system, which is elastomeric bearing and sliding bearing system. And we can note that we can using the elastomeric bearing in every most of the what I will say most of the bridges. Okay, let's see. The elastomeric bearing system, the low damping natural frequency and cynetic rubber bearing, and high damper natural rubber bearing, and lead to rubber bearing, and low damping natural rubber will lead to the core. So we can see here the elastomeric bearing is natural or high damper rubber bearing, and this is the one. Here is the internal steel seam, we can see here, and here is the rubber, and upper portion is mounted in the plate, and another is the LBM, which is led to the core, we can see here, and another is a rubber, we can see the here, and the upper portion will be used mounted in plate, and internally we can use internal steel seam, and here, and we can see here the some of the information is given here. The high damper rubber bearing as two type of, and lead rubber is there. Here is the sliding bearing system. As we are completing here the elastomeric bearing, I will show how to calculate the elastomeric bearing in earlier, as we've been seen any kind of if any, this is the stiffness of elastomeric bearing. We can use this formula, K equal to G into S. So G is given, which is a modulus of rigidity. A is a area, and S is the height of the building. Then we can use we can calculate the stiffness of elastomeric bearing. So I will see the my calculation here. So sliding bearing system, we can see. Now we'll go to the sliding bearing system. Here is the building foundation. We can see this is the building foundation, and this is the column base, and spherical slide bearing we can see here, and the sliding will be this, rotating will be this in this direction. Okay, we can see the combined bearing system is also here, um, and then the tune. So these are the inlet here. The base isolation system is inlet. I'll see here the elastomeric bearing system calculation in deeply. So another we can see the TMD, which is tunic mass damper, and liquid mass damper is very deeply. So TMD we can see here the tunic mass damper in Taipei 101. So it is using in Taipei 101, which is beside of the China. So this is the in this building we have been seeing the TMD is using, and at the top of the building we can see here for controlling the natural frequencies. So Taipei 1, we can see here Taipei 101 is designed with the 660 ton steel pendulum that was used as a TMD as a cost of US 4 billion million. So this is the huge, and suspended from a 19 to 18 floor. So it is 19 to 18 floor, and the pendulum so to offshore movement of building causes the strong gases, and it is spare and the highest damper spare in the world, and consists of the 41 cellular steel plate and bearing, and each of the 45 millimeter 125 millimeter thick, and while together from 5.5 meter. We can see here on August 2015, strong wind from the typhoon saw the main damper of 100 centimeter, which is 39 inches, and largest movement ever recorded in damper, and damper has become the such the hottest tourist attraction. Okay, so we can see here the TMD damper is Millennium Bridge in London. So we can see the TMD is inserted on bridges. Okay, so another we can see tuned liquid damper. We can see the Nagasaki Airport Tower, so using the TMD liquid damper, and another is the Yokohama Marine Tower, and the structural response is like that. The structural response we can see here. A is a centimeter, H is 3 centimeter, and mu equals 0.885. Here is the okay. So the tunic liquid damper is Japan, and the structural response we can see here. Okay, so in this way the tunic and um, TMD and TLD is completed. Now we'll see the hybrid control. Here is the hybrid control is as we have been seen the we know the hybrid is a combination of active and passive. The hybrid control is combination of active passive control system incorporated advantage both. So hybrid mesh damper system we can see here is the graph. If we see the hybrid mesh damper system in natural response, this is the natural response is axis is frequency, y axis is amplitude, centimeter per second square. Here is the Sandagaya Sandagaya Intel building. We have been seeing this building, and top view of the HMD. This is the top building, and inserting this HEM, which is hybrid mass damper. Here I'm just skipping. So hybrid control, there is a hybrid mesh damper system and metallurgical. So these are the induction. Now we'll see the metallurgical damper system. So let's see. Here's a metallurgical damper system, and MR fluid particle in magnetic field. We can see here. A metallurgical damper or Torheological shock absorb in a damper field with um, magnetorical fluid, which is controlled by the magnetic field, usually using electromagnet. Okay, so these are the electromagnetic using. We can see here the Cornell one and magnetic particle weapon here, And if we see on the picture the various features of the MR damper, which is one is fluid, so fluid, and another one is constituent, and another one force, and last one is lab and field application. Okay, these are the magnetic field. So in this way I have completed all the what I will say the theory. Now we'll say the practical application. As a engineer, you have to know the practical problem of the vibration control. Okay, so let's see. Okay, this is the first math we have been seeing here. Here is some given data is here. Calculate the lateral stiffness. The elastomeric bearing system with shear modulus is given 100 psi, and bearing area is given 100 inch square and height of 10 inch. Okay, so we have to calculate the shear. An RC shear wall with young modulus is given 30 psi, and D is 120, and thickness is 8 inch square. So height is 120 feet, which is 10 feet, and these are the 10 feet. Okay, so at first we are calculating lateral stiffness of elastomertic bearing, which is we know K equal to G into H. G is modulus of rigidity as a area of the elastomertic bearing, and H is the given in height of the elastomertic bearing. So in this way we have found 1000 pound inch. Okay, so we can see here the lateral stiffness of shear wall. When one end is fixed and another one is free, or like cantilever, if we think in cantilever, then it will be E into T 4H cube plus 3H into T, and found this below. And when we consider when both ends are fixed, then the slab will be above of the shear wall. So we can using this formula and found 6 into 10 to the power 6 pound per inch. So we can using this formula also as a cantilever system. So these are the answer of the shear wall use. So we have been calculating the shear stiffness. Okay, lateral stiffness. Now we can see another example, which is given a 5% damper single story, which is 10 feet by 15 feet by 10 feet floor column system weighting 200 psm including all loads, is supplied by 220 diameter of RC column. Each column is 10 height as shown in figure. These are the figure. 10 feet and 2 inch dia of column is given. This is the 15 and 10 inch dia of the bracing we have been seeing. Ground motion 1 and ground motion 2. Picture 1 and 2 is given here. In picture 1, this is the picture 1. Given K, which is structural stiffness, sum of K is given 12 pi by L cube, and E is given here, and M naught is a structural mass, and flow divided by G, and C equal to 2 psi root over K, and psi equal to given 5% of damping. So the system is stiffened by two massless RC cross bracing. Here is the cross bracing. The massless bracing is figure 2. This figure is given to length is given 15 feet and ly is 10 feet. This is the 15 feet and ly is 10 feet. We have been known here. And 10 inches diameter. Each of the stiffness we are calculating EA by L, and damping is given here. And we have to calculate determine the natural frequency and damping ratio of the system. So in this way. And another one, we have to use the proposed PNBC response spectrum Z S1 and TB value is given, and TC is here and TD is given, to calculate the elastic peak deformation and base shear. Okay, and another one, we have to compare the result from 2 which is found is here, and corresponding value for original step. Okay, let's start. So we know the W is given, floor area into UTL. As UTL we have been found 20 PSF, In this way we have been, and floor area 10 into 15 into 10 is given here. So in this way we can found the weight, which is 30k. So if we divide it in by g, then it will be mass, and found this value, and e is given, and I equal to, the as the circular column, so it will be pi d to the by 64, and found this value. Now we can see calculate the k, which is 12 pi by l cube, is given in question 12 pi by l, and it will use it for column also. And we are calculating k, which is given the two column we have been seeing, column 1 and column 2. That's why we are using summation of k is here 2, and we are calculating natural frequency, which is known root over k by m, and found this value. And for time period we know that 2 pi into omega, or natural frequency, and which is found 0 pi, this value. Okay, so this value, this formula only for single degree of freedom. So damping C, we know that 2 psi root over k by m, which is 1.50. As we know the T, which is 0, greater than, we have been found this value, which is 0.09, which is greater than 0 but less than 0.5. So in this way the condition is, if the condition is satisfied, then we can use the spectrum coefficient C, this condition. I will get it is depend of the it is depend on the time. If the time of is different, then the value will be changed. If you go to the if you go to sorry for interrupting you. If you go to the previous ones, then you can find the how we'll get this. Okay, let's see how we'll get this. There are lots of there is a lots of what I will say, this I'm coming here, this, so it this C, the what I will say, the calculation of C is depends of the this formula, which is 0 t Tn into Tb, which if the condition is satisfied, then we can use this formula. So if we see the Tn is greater than 0 but less than Tb, so less than Tb, this, so that's why we are using first formula. So this formula. If we will see the T naught, we have been found greater than Tb but less than Tc, then we can use this formula. So in this way we have been selecting this formula and found 1.97. So elastic base shear will be to ZIC ZC into W, which is 7.88, and elastic peak deformation we know K, P equal to Ku, and in this way we will putting all these value and found that displacement is 0.024 inches square. Okay, so let's see another, we can see here graph LB equal to root over, we can just, if we calculating this length, then it will be hypotenuse equation root over 10 square plus 15 square. We can in this way we can use the bracing length, which is 18.08, and Sx we can say Rx equal to A by L, which is found 10.010. So if we calculate K equal to K net 2, as we have been using 2 bracing and cos theta. Why we have been using cos theta? Because of nothing but, as we have been seeing K equal to Sx equal to C square CS S square. So we can see the graph is these are the intersect this point, and these are the calling C square. So in this way the formula is coming, but it is the constant formula. You have to memorize this formula. Okay, but you can reduce this number to, if the column bracing is 3, then you can use 3, but as usually bracing is 2 bracing, that's why using 2. Okay, and in this way you have been found the value of K. So if we see in without bracing the stiffness was 3 to 7 kip inch square. So if you go to the 3 to 7, where is the stiffness? 3 to 7, this 3 to 7, these are the without the stiffness or without using the bracing, without using bracing on the on the structure. When we using the bracing, then you can see the stiffness is increasing. Okay. Okay. So that means if we push the 1038 keep load, then 1 inch will be deflected when using the bracing. On the other hand, we have been using here when we insert when we force insert the force 320 keep force, then 1 inch will be deflected. So we can see the 1 inch will be deflected only 3 to 7 keep when unbracing, but when we use the bracing, that it will be 6 times if we want to sway or deflect at 1 inch also. Okay, let's see the natural frequency root over K by N, and found and time period we have been seen to shy at to or I will say 2 pi root over M, and found 0.041. So if we see in previously the without bracing the TL equal to 0.07, but when we inserting the bracing, the time period is 0.04. So you can see the time period will be reduced. So these are the time period we can from 0.09 without using bracing. But when we using the bracing, then the time period will also reduce. Okay, so we can use another damping ratio. We can see here the C will be C naught plus CA, which is 2 root over psi n and found 1.69, and damping we equal to root over C into root over K by M and found which is 7.06, and eta will be 10 into root over 10 divided 5 by psi, and psi is found 7.07, which is 0.91. Now we can see here time period we have already found 0.04, which is greater than 0 but less than TB. That's why we will using this value, but just value of psi will be changed and found 1.35. So elastic shear 2 by 3 ZCW we have been done 5.4, and elastic peak deformation equal to no P equal to K delta or KU, and delta or U deflection we have been found 0.0. So we can see without bracing the deflection was 0.024. When using the bracing, and then the deflection will be 0.04. So you can see when we inserting bracing, then it will reduce the deflection, which are less than 1 by 8 times. So we can see using bracing is very good for controlling deflection. So as we using deflection bracing, then we have been found 0.03 deflection. On the other hand, we have been seen in previously calculation here, we have been found 0.021 without bracing. There is no bracing on the structure. 0.024 and when we using the bracing, then we have been found 0.03, which is 1 by 3 times less. It is reduce the deflection also. So we can conclude that bracing and shear wall it is reduce the deformation. Okay, let's see another example here. The structure shown in figure 1, this is the figure 1, isolated. So you can see here here is the mass 1 K to C and M to K to C, uh, the supported on massless base isolating system in shown figure 3. Here is a figure 3 massless, and the stiffness kb equal to the 1/10, so it will be given 1/10 kb or k2 of the stiffness if original structure which is m is given 0 and kb equal to 1 by kb equal to k naught divided by initial divided by 10. Okay, determine the first natural frequency and modal shape of the system. Okay, second we have to calculate the use of the proposed BMPC 2020 spectrum, which is given z as s1 tb tc and tt, and we have to calculate the elastic peak deformation and base shear of the base isolation system for the first mode of the vibration. Okay, let's see. Here is a figure 3 we have been seeing here, and this is the massless figure. We have been using the equation or equal sign. So m2 is given 0.02, k2 equal to is given, and all the data will be given in question. So we know the k equal to k1 plus k2 minus k2 minus k2 and k2, and in this way we are putting all this value. And m we know the m1 0 0 m2, and in this way using this formula. Now we are using this equation which is k minus omega square equal to m. So these are the k. So we have been using this k, this value, and minus and this equation. So I'm just skipping maybe 10 10 or 3 lines, and after that skipping 3 lines we are getting this equation. If we using this 3 equation, then the time will be needed more, as we need as we reduce the time. That's why we are just skipping. But if you want to do it, then you can using this. So how will you find this? You just using 3599.2 minus 0 and 327. Here is a 327 minus omega square into 0.003, which is m, and minus and 32. Here is a 32 7.2 minus 0. You just using here, or you can use this approaches. If you taking here with here this here, then what will be 0 0 0 and 0.77. Then you can use this in this way. In this way you can calculating here. After that using calculation calculated, then you can find the natural frequency with 19.58 radian. But you can memorize these tricks for reducing some lines. And time period we can found 0.32. Okay, so now we are using for modal shape, we are using this formula. I will get, we have been already found this formula is here. You can see here 392.92 shape 1 minus shape 2. These are the shape 1, and if we taking the ratio, then it will be 1 divided 1.5. What this mean is, if the first mode is giving 1, then second mode will be gone 1.1. Okay, so let's see another example. What does mean it? It does mean what does mean it? If the spring deflected in 10 inches, then whole structure will be deflect only 1 inches, because in this way you can see the almost deformation are taking at firstly spring. We can see at firstly almost deformation are taking here. Here is you can see only 0.1 deformation taking on the structure. So if we calculate in the whole if we calculate the whole deformation is 11 inches, then we can say the 10 inches will be taken at firstly 10 inches taken in the spring, we can say spring, and then and the remaining 1 inch will be taken one last will be occurred in the structure. So these are the main phenomena using as per from this calculation. Okay, so let's see here another example. The structure is shown in figure 1. This is the figure 1. Figure is given TMD. Okay, support in TMD, tunic mass damper, is figure 4. This is the figure 4, it's given here, and mass MT and stiffness KT, and the damping CT is given by these are the also MT equal to 10th of M naught, M initial, and KT equal to K naught by 10, which is 10 times less than 10 times, and CT equal to CM. For the first mode of vibration, we have to determine the nature of frequency, modal shape, damping ratio of the system, and compare the result 1 and 3 and corresponding below the original structure. We have been seen here M2 is given 10 times of initial M1, and K2 equal to 10 times of less than K naught. Okay, so let's see. K1 is given 3 to 7 in we have been found in previously calculation is given, it is also given, but if we calculate here in previously we have been calculated here 3 to 7, so in this way we are just taking this value for calculating purpose 3 to 7, and M1 is given also, C1 also given, and K2 equal to less than 10 times and divided by 10 times, and M2 equal to also divided by 10 times, and C2, CT, and C0 equal to 0.5. So we know K equal to K1 plus K2 minus K2 minus K2 and K2, and M equal to M1 and 0 0 M2. Now we are calculating here K minus omega square equal to M. So if we go taking this M is here, and then will be some value will be here, there will be 0, there will be 0, and 0.007 is here, 0.007 is here. So if we calculating here, we just skipping 3 and 4 lines, and after then we will get this below. I will get 359.5. This is the below 359.5 minus omega square. This is the minus omega square, and 0.07. These are the 0.07 minus 32.72. These are the 3. There is a plus 32.72 minus omega. This is the formula omega, and minus 0.007. These are the 0.007, and minus 3.32 and minus 3.32 into minus 0 and 3.32 and minus 0. In this way we are producing this equation for time consuming. So you have to apply this strategy for taking the less time. Otherwise you will need the more and more time. Okay, so if we putting this value on calculator, actually this calculator I have been used this here. If we apply all the parameters here, and we will find 73 radian per second. So these are the natural frequency, and time period will be using this formula 0.0837. Now model shape we have been seeing minus K into omega square into M into 5 omega natural period we have been found to 76. Putting all this value and the shape factor phi will be remain same. Okay, so these are the formula we are using this in this here. We just taking this formula is here, 395 minus omega into 0.007, just inserting shape factor 1 minus 3.3. These are the taken minus into minus, it will be plus, that's why we can use plus, and multiplied with shape factor 2. And second one we can see here, this is the second one, 359 minus 76. How will get the 76? 76 is omega. We are just putting this value in omega. We've been seeing the omega 76. We just putting here and finding this is the equation. So we're not equating. Thus, if we go to taking this here in right side, then it will be like this, and we are taking the proportion of psi 1 phi 1 divided by phi 2, which is the shape factor, and we have been seeing 1 is 2 minus 2.7. This are the 1 and minus 2 is reverse direction. So these are the we have been found here, and now we'll calculate the C.50 is given in equation, and C2 is also given. We know the C is the stiffness matrix C1 plus C2 minus C2 minus C2 C2, and using this here, then we know the M1 0 0 and 2, and found this way. If we use model mass, then we will see M psi factor M into psi, and in this way we will be sure the psi is found 1 minus 2.0 is here, 1 minus 2.7, and M is found is here. This is the M are taking here, and psi we have this T means transverse, and these are the psi phi, these are the main phi, 1 minus 2.7, here is a 1 minus 2.7, and this T is transverse, so we have been transverse is here. After this we can using only this, we are completing this matrix. It will be like this, 1 into 0.7, these are the 1, and multiply with 0.07, and plus 2 minus 2.0 into 0, and these are the here into this 1 into 0, 1 into 0, and plus minus 2 into minus 2.007, and it will be remain same. And in this way we are calculating here and found this value, and we are calculating here and found this value. Now we are calculating here 0.007 into 1, 0.007 into 0.007 into 1, and 0.002 into minus 2.7, 0.02 minus 2.7, and in this way we can found 0.1343. Now we can see model dumping C phi transverse C into phi, and we have been used as usual here. Now we are the stiffness matrix emerging here, and found this below. At first we are taking this into this, and this into this, and found this below. Now we are calculating second one, this into this into this found here, and 2 minus 2.7 into 5, and found this, and these are the remain same as it is, and found these are the form 2.35, and this is the minus 1.8. Now we're calculating here as usual, and found 7.34. So model dumping ratio psi, we know the C equal to 2 C divided by 2 omega into M, or we can use this, and found this value, which is 36%. So you can see if we using a TMD, so dumping ratio is increased from 5% to 36%. So if you go to the previously, then we have been seeing the dumping ratio is 5%. Where the phi, this where the value of psi, this is the 5%, 0.05, or the psi, this is the psi, is 0.05. Psi is 0.05, and we are using C value of psi. These are the 36%. The psi was 5%, now is constant, and increasing 36%. So if we summarize that, this is the summary. The original structure, the damping was 5%. When using the bracing, the damping psi is 7.07%. It is increased. When we using TMD, technical damper, then the damping ratio psi is increased also 36%. So these are our main summary. Okay, so let's see another example here. These are the last example in our math. So the superstructure and substructure of bridge is being supported 3 RC spare, each of the 20 feet. These are the we can say the real problem in Padma bridge. We can see 6 pile is used and is 200 long and 10-meter dia. The structural mass consists of 10 feet long RC pier, average section we can say 15 feet into 5 feet, and 500 long bridge deck waiting to keep pier per feet. The superstructure of bridge supported on mass/bridge isolation spring with shear modulus 150 PSN and bearing area 34 feet square. The height is 12 inch. Here MD and MP represent the mass. Here is the MD and MP represent the bridge deck and pier. This is the deck and pier. D means deck and P means pier. While KB and KP are the stiffness of page isolation of pier. So we have to firstly calculate the lateral stiffness of page isolation system. Then we have to determine the fastness or frequency of the mode shape of the system, and then we have to use the new PNBC or ASC318 or ASC705 in zone 2 for soil SB and damping ratio 5 to calculate the base shear and elastic deformation of fast mode of vibration of the system. So let's see the solution. Here is the KB, which is the elastomeric bearing system. We know K B equal to G into H, and G is given modulus of elasticity, and bearing system is given, and H equal to 20, and found this way. And number 2, these are the first one. We calculate the lateral stiffness of page isolation. Number 2, determine the fastness or frequency and mode shape. So we know the KB equal to given 61. So we have been seen here. It is given, and MD is 0, and WP we know the length is 500 feet. These are the 500 feet long, and 20 is UTL is given in UTL, which is 20 is given UTL, so it will be mass, and 150 into 5. These are the volume. 150 into 5. So we know the 100. This is the 100, and 50 into 5 is given. 100 feet is a long with RC pier, and average section is given also. Yeah. Okay. And the unit weight of concrete is given 1.5 and found 1112 by K. And MP, which is the pier, mass of the pier, we know. This is the weight of pier, and mass of the pier will be divided by G, which is acceleration or gravity, and found this value. And ECU, we know the concrete modulus of elasticity is given here, and I is pi t to the power 4 by 64, which is the circular pi, and found this value. And KP, we know that 12 pi by L cube L, and number of piles, as we have been solving the pile system with the 6 pile. We know the 6 pile have been used in this case. So this we have been used 6 pile, and the height of the EM pi list 200 is given in question. Weapons in 200 feet, and it is converted to the inches. That's why we multiply 12 and found this value. All the direction is given here. This all the data is given here, and found 159 point keeping system. Now draw the diagram. So now we'll draw the diagram here. MB KP M1 K1 MP here. Now we'll see here K equal to K1 plus K2 minus K2 minus K2 and K2, and putting find this value. M equal to M1 0 0 M2, and we'll found here. Now natural frequency we were using here K minus omega into M. So if we use minus omega into M value is here. If we go taking here, then after taking here, then we have found this value. How we get? We are skipping the three equation. That's why we're taking it. You have to memorize this for reducing calculation. How will get? This is the 2 to 3 minus 2 to 3 minus K minus omega. Where is the minus omega? As we have been used minus omega into M. M is given to 28.9 into 61. We have been seeing here 61 into 0, and minus 61. This is the minus 61 into 0, and minus 61. This is the minus 61 into 0. And using this way, we have been calculating omega. We've been using this calculator, using just all the values here, then putting natural frequency 2.35 radian per second by calculation, and the time period we can from 2.67 second. For the mass shape, we have been shown K into K minus omega square into M into M into phi. Thus putting this value here. These are the equation we have been found in previously from taking here and 280 and using phi, and minus into 60 into phi. And just we are using the value of omega, as we have been omega is found 2.35, just using 2.35 here, and we have just a proportion of this equation and found omega psi 1 and psi 2, which is 1 and 1.002. This will be fine. Sorry that. So if we seen that here the first story giving 1 and second story is giving 0.002. Is a minor. I'm using that value. Okay, so I hope that it is also completed. So if you have any question, then let me know. I'll clarify you. So if we recap this, then we can see and summary is when the original structure is taken a damping ratio 5%, but when we are inserting in the bracing, then the psi value will be increased 0.07. When using TMD, which is tuning muscle damper, then it will be also increased with 36%. And another example we've been seeing here, the summary. The total structure when we are using the spring, then we can see the spring is taking almost all the deflection. Here the another example we've been seeing here. When we not using any kind of pressing, then the deflection was 0.02. When we using the bracing, the deflection also reduced, which is 0.003, which is 1.18 less than 1.8%. Okay. So you can see here calculation. So if you have any question, then let me know. I will try to convince you. I'll try to answer your question. Thank you everyone. Thank you for your patience.